Hey everybody, welcome back to another video. So today we're going to be talking about EPSPs, subthreshold EPSPs, and spiking activity in LTD induction. Now before we begin, we will briefly repeat some important information. Now, as we all know, the dorsal cochlear nucleus is the first auditory brainstem center that also integrates multisensory inputs. Now, multisensory inputs are also integrated further up the auditory pathway, like in the inferior colliculus, but the DCN is the very first, so to speak, the first step. Now, the principal cells in the dorsal cochlear nucleus are the fusiform cells, which are also called pyramid cells. Now, principal cells are the main functional cells within a specific tissue, organ, or nucleus. If you guys don't remember what a nucleus is, in the context of the brain and nervous system, a nucleus is a cluster of neurons or nerve cells in the central nervous system that are organized together to perform a specific function. And in the context of the dorsal cochlear nucleus, the cluster of neurons here are responsible for processing and integrating multi-sensory inputs into the auditory pathway. The reasons for this are explained in my previous videos, but up on the screen you can see the different clusters of neurons that are in the dorsal cochlear nucleus. The molecular domain is what you see on the very surface of the dorsal cochlear nucleus, and the deep layer domain is, as you can understand, a deeper layer, obviously. Now let's take a closer look at the illustration up on the screen. So the pink box you can see is the granule domain. And the granule cells, or the GRC, as you can see, the kind of little star, these are the small excitatory or glutamatergic neurons that lie in the granule cell layer. And their axons ascend into the molecular layer, where they run longitudinally as parallel fibers, and they provide excitatory input to other DCN neurons. The parallel fibers are labeled as PF on the illustration. Now next are the unipolar brush cells, or UBC, and they are also excitatory or glutamatergic neurons. The UBCs receive excitatory input, shown by black circles, from the mossy fibers, or the MF, and relay that excitation to the granule cells. Now, the Golgi cells, labeled as GOC, or the orange circle with the two outstretched arms, they are inhibitory interneurons, specifically GABAergic, and they help regulate the granule cell activity by providing feedback inhibition within the granule cell domain. So they're kind of similar to cartwheel cells in the case that they provide this inhibition to the excitatory neurons. Now a bit more about the mossy fibers. These are afferent fibers that bring excitatory inputs from various sources, like the auditory nerve collaterals or other brainstem nuclei. And they contact granule cells and unipolar brush cells, as you can see on the diagram. Now let's move on to the molecular domain. Now again, on the parallel fibers, if you guys remember what I just said, they are the ascending axons of granule cells, and they fan out here. So they make the excitatory, or the black dot, synapses onto the dendrites of several cell types in the molecular layer, including the cartwheel cells, the fusiform cells, and the stellate cells. Now, if you guys remember, the cartwheel cells, which are labeled as CW, are the large inhibitory interneurons, and they receive excitatory input from the parallel fibers, and also, in turn, make inhibitory synapses onto the other neurons, especially the fusiform cells labeled as FC, and sometimes each other. As you can see, the cartwheel cells send inhibitory signals back to the fusiform cells, or the principal neurons, and this forms the classic feedback inhibition loop, where the activity of neurons in the circuit regulates itself to prevent overexcitation. And as you guys remember, the excitatory and inhibitory disbalance in tinnitus is a very, very prevalent factor. And the stellate cells labeled as SC are another type of inhibitory interneuron in the molecular layer, and they also receive the input from parallel fibers, and they project locally to help modulate the excitability of the fusiform cell. As you can see, there's a very complex mix of feed-forward and feedback inhibition in the dorsal cochlear nucleus. So if you guys remember, feed-forward inhibition occurs when an excitatory neuron activates an inhibitory interneuron, and this interneuron then inhibits a downstream target before the excitatory signal gets too strong. And in the dorsal cochlear nucleus, feed-forward inhibition involves, of course, the parallel fibers, or the axons from the granule cells, and these fibers excite the stellate cells and the cartwheel cells, which are inhibitory interneurons. And then these inhibitory interneurons then suppress the activity in the fusiform cells. This is basically another layer of refinement of the input to avoid excessive excitation. Now, if we talk about feedback inhibition, the definition of it is when a neuron sends signals to an inhibitory interneuron, and that interneuron then sends the inhibition back to the original neuron or other neurons in the same circuit. Now, in the dorsal cochlear nucleus, there's no well-established feedback loop in which the fusiform cells re-excite cartwheel cells directly. Now, on this chart, it can look like feedback at first glance because the cartwheel cell projects back onto the fusiform cell. But cartwheel cells are mainly excited by the parallel fibers or the ascending axons of the granule cells. They do not receive direct excitatory synapses from fusiform cells themselves. Feed-forward inhibition occurs when the same excitatory input, the parallel fibers that drive the principal neuron or the fusiform cell, also excite the interneuron or the cartwheel cell, which in turn inhibits that principal neuron. And feedback inhibition would require the principal neuron or the fusiform cell to excite the interneuron directly, or the cartwheel cell, which then loops back to inhibit the same principal neuron. And on the diagram, even though the arrows kind of look backward, the circuit is still feed forward in terms of functional flow. For example, the parallel fibers are excitatory onto cartwheel cells, which are then inhibitory to the fusiform cells. Or the parallel fibers are excitatory to fusiform cells too. So even though it might look like it is feedback inhibition, it indeed is not, because the inhibitory drive is triggered by the granule cell or parallel fiber input rather than by the fusiform cells themselves. It's considered feed-forward inhibition than true feedback. If we take a look at this, for example, Renshaw cell circuit, which is an inhibitory interneuron in the spinal cord, we can see that the alpha motor neuron sends a recurrent collateral or an offshoot of its own axon to the Renshaw cell. And this synapse is excitatory, meaning the alpha motor neuron activates the Renshaw cell directly. And the Renshaw cell, once excited, sends the inhibitory output back to the same alpha motor neuron, and sometimes neighboring motor neurons as well. And this means that the alpha motor neuron is controlling its own inhibition via the Renshaw cell. If we're talking about maybe retrogrades or maybe some indirect feedback, in some brain regions, retrograde messengers like endocannabinoids or nitric oxide released by the postsynaptic neurons can modulate the presynaptic terminals, but in the DCN, they're not typically depicted as major circuit pathway or for fusiform to cartwheel feedback. Now, if we go back to the diagram, the vertical cells, as you guys remember, are the inhibitory neurons in the deep layers that also, of course, contribute to shaping the output by providing the inhibitory input onto the fusiform cells. And they also receive excitatory input from the auditory nerve fibers, as you can see. My belief is that the vertical cells are strongly involved in the suppression of tinnitus, for example, from cochlear implants. It would be a vast oversimplification to say that exclusively vertical cells are responsible for this. It's most likely more accurate to say that both types of DCN interneurons, like the cartwheel cells and the vertical cells, are responsible for restoring this excitatory and inhibitory balance, or the inhibitory networks becoming re-engaged, for example, decreasing the spontaneous firing rates of fusiform cells and potentially desynchronization or desynchronizing the fusiform cell clusters that are firing together and being recognized as a significant auditory event by the higher centers. Now back to the diagram, the D-stellate from the VCN, this refers to the inputs from the D-stellate cells in the ventral cochlear nucleus, and D-stellate neurons are glycinergic, so their projections provide inhibitory input to the fusiform cells. Considering the ventral cochlear nucleus also receives excitatory input from the auditory nerve fibers and the parallel fibers, there is a chance that this could also be a mechanism involved, or the feedforward inhibition from the VCN through the D-stellates could also potentially be a mechanism involved in the Susan Shore device, suppressing tinnitus. Now, if you move back to EPSPs, or excitatory postsynaptic potential. Now, what an excitatory postsynaptic potential is, it is a very small depolarization of the postsynaptic neuron. For those who are not aware of the terminology, the membrane potential can shift slightly if there is a small amount of excitatory drive from the presynaptic neuron to the postsynaptic neuron. So for essence, when a nerve signal reaches the or the axon terminal or the presynaptic terminal of the neuron, the neurotransmitters are released, the excitatory neurotransmitters, for example, and the neurotransmitters bind to the ligand-gated ion channels, and they cause a small amount or a certain amount of positively charged ions like sodium to flow into the postsynaptic neuron. And this makes the inside of the neuron slightly less negative, bringing it closer to the threshold needed to trigger an action potential. Basically, in short, EPSPs are small boosts of increased membrane potential that help the neuron get closer to firing, and of course passing the signal on to the next neuron. If anybody is still confused about why an action potential occurs or may not occur, the ligand-gated ion channels basically only open during the binding of a neurotransmitter like glutamate binding to AMPA receptors. For example, AMPA receptors are ligand-gated ion channels. And these ligand-gated ion channels open up and allow for a small depolarization, like I mentioned before, or a small influx of, for example, sodium ions. And the neuron is quote-unquote programmed in such a way that the voltage-gated ion channels open in response to a certain voltage being reached. So that's exactly what this threshold is. Yeah, so the full, I guess you could say, step by step, is the neurotransmitters are released into the synaptic cleft from the presynaptic terminal. The neurotransmitters, for example, glutamate, bind to the AMPA receptors, and then the AMPA receptors open up, allowing a small amount of, for example, sodium influx. And when this sodium influx occurs, the membrane potential becomes slightly more positive, and if it becomes positive enough to a certain level, the voltage-gated sodium channels that open during the threshold being reached have a property called voltage sensitivity. And these channels, the voltage-gated ion channels, have specialized proteins that change shape, will allow the voltage-gated ion channels to open up, and there's a lot of them. And this, of course, will lead to the massive depolarization or the massive influx of sodium ions into the cell, which of course is the action potential itself, or the nerve signal. So if we're talking about subthreshold EPSPs, a subthreshold EPSP is an excitatory postsynaptic potential that does not trigger a postsynaptic spike. Now, from experiments done by both Susan and by Thanos, papers will be linked in the citations. These EPSPs, or these subthreshold EPSPs, play a very major role in inducing LTD at the fusiform cell synapses. And in most experiments, an EPSP from a parallel fiber, if not followed by a fusiform cell action potential, tends to weaken the synapse over time. And on the other hand, if the same EPSP is closely followed by a postsynaptic spike, within a narrow window, it leads to the strengthening, or LTP. And this means that LTD or long-term synaptic depression, is associated more with EPSPs that remain subthreshold, or the input is not validated by an output spike. Now, why would failing to fire cause synaptic depression? Well, the underlying reason involves, of course, the timing of the intracellular signals, especially calcium, as we know, the calcium signaling pathways. A subthreshold EPSP still depolarizes the dendrite a bit and activates the receptors, the NMDA receptors. But without a spike, the neuron's depolarization is limited and very brief. And this scenario tends to produce a modest calcium influx, not a massive calcium influx, like with rapid spiking or pre-post timing. So it produces the modest calcium influx through the NMDA receptors, and possibly voltage-gated calcium channels that preferentially triggers the depression pathways. Now, in contrast, a spike, especially a back-propagating action potential combined with the EPSP, causes a larger calcium transient that favors the potentiation pathways. Now, I'm not going to go into detail because I already talked about calcium signaling pathways, but I will probably make a video more in depth about the activation of the calcineurin or the phosphatases and the CAMK2. But basically, the absence of spiking during the input, or when a spike comes before the input, tells the cell that the input was not effective or was predictable, and the synapse is down-weighted. And the experiments done by Susan Shore and Thanos in vitro confirmed it. When the parallel fiber stimulation was not paired with the postsynaptic firing, the fusiform cell EPSPs became persistently smaller, whereas pairing the EPSPs with the postsynaptic spikes caused the EPSPs to grow, or long-term potentiation. Basically, altogether, LTD in fusiform cells is induced by the subthreshold or unreinforced EPSPs rather than by strong spiking activity, which is a very important key feature that differentiates the weakening versus strengthening of the synapses. Now, what does this mean for us and for the Susan Shore device usage? Well, unfortunately, there's no way to know if the EPSP is subthreshold. I'm talking from the parallel fibers to the fusiform cell, or the SP5 or trigeminal cervical complex input onto the fusiform cell. So the best thing that we can possibly do is to make sure that during the device usage or during the stimulation, that the stimulation is as weak, or the somatosensory stimulation is as weak as it possibly can be. Which means, for example, titrating the stimulation to the user's perceptible thresholds. Now, whether or not having the somatosensory stimulation below perceivable thresholds is a viable option is yet to be seen, but I assume that it could work as well. So pretty much what that means is that cranking up the somatosensory stimulation to the max is not a good idea, because this can introduce very strong EPSPs that could potentially depolarize the fusiform cells to a point where it would be like a post pre-pairing, meaning it would favor strengthening or synaptic strengthening rather than synaptic weakening. An example of strong EPSPs from the SP5 or the spinal trigeminal nucleus onto the fusiform cells would be somatosensory modulations. So when you bend your neck, or you flex your jaw, or you yawn, or something like that, this causes enough excitatory postsynaptic potential to lead to the threshold being reached in the fusiform cells to fire a spike, or to fire an action potential, So when you are doing a somatosensory modulation, you are doing exactly what I described previously. You are causing a temporary increase in the firing rates of the synchronized fusiform cell clusters, which means, of course, your tinnitus becomes louder briefly, while these excitatory postsynaptic potentials from the parallel fibers are reaching the threshold for more intense spiking or action potentials. So when using the Susan Shore device, it is absolutely very crucial that you do not use too strong auditory stimulus, especially if it's high frequency, due to the rapid firing of neurons during rate coding. If we're talking about the auditory nerve fiber input, and that the somatosensory stimulation is as low as possible as to not introduce strong excitatory postsynaptic potentials. Too strong auditory stimulation and too strong somatosensory stimulation could potentially lead to the calcium spikes being too strong, or rapid, which would favor LTP instead of LTD, which is probably the reason why some people potentially could spike from the Susan Shore device. But if you're careful, of course, this will not happen. That's basically everything I wanted to say today. Calcium signaling video coming soon. And for any updates on basically on anything, including my trials or whatever, or any other discussions, you can, of course, join my Discord server in the description.